All right, good morning, everyone. Today we're going to be finishing up 4.2. But before we do that, let's do a little bit of a recap from yesterday. So yesterday, we talked about how we can approximate a region under a curve using rectangles, either an inscribed rectangle or a circumscribed rectangle. Sorry, inscribed here, circumscribed here, either an upper sum or lower sum, either an over approximation or under approximation. And just to review some of the process that we used here. First thing is identifying the width of each of our intervals. So width is going to be b minus a over n, right endpoint minus left endpoint divided by the number of rectangles. And after we find that width, we went ahead and we started to find the x value intervals that we'll be using. So we started at the left endpoint, which is 0, and we added the width. So as we add the width, we're able to find the next value over. We add the width again. We add the width again from 1 to 1 plus 1/2 gives us 3/2. Add the width again, 3/2 plus 1/2 is 2. Okay. And then we went through and we found the width and height, or something that represents the width and height for each of the rectangles. All right, for this one, we were doing an upper sum. So for the first rectangle, we're choosing the higher of the two values between f of 0 and f of 1. So we chose f of 1 to represent the height of the first rectangle. Sorry, f of 1/2 to represent the height of the first rectangle. So then we just did f of 1/2 times 1/2, that's the width and height, plus width and height, width times height here, and then width times height. After we got it into function notation, then we had to put these x values into the function to get the respective y values, and then we're able to merge them together and get down to a numeric value. In this case, this represented an over approximation of the actual area. We did a similar thing with lower sum, but instead of choosing the higher of the two y values, we chose the lower of the two y values. So between f of 0 and f of 1/2, we decided to choose f of 0. So f of 0 is now going to represent the height of the first rectangle, which is lower than f of 1/2, which is the height of the first upper sum rectangle. Now, a lot of these are repeated between upper sum and lower sum, but they are kind of staggered. Each of these represent a different part of the rectangle. So that's why we end up with a lower sum here and the upper sum 5.75. The reason also I wanted to repeat going over this process is because today we're going to see how all these steps is all going to be kind of merged into a formula as we explore moving from approximation to exact area of a region. Okay, so I'm going to come back and kind of show how all this is kind of being merged and automated into a formula where we don't have to do all these steps if we're finding exact area. Okay. So today we're going to be finding exact area using limits. Let's start with an approximation of a region. Okay, so let's say we're using 4 rectangles to approximate the area of a region. And we see that it's doing a decent job. Obviously, it's not perfect. There's significant gaps that we see. That is not fully giving us a perfect approximation or a really good approximation. But even though this is doing a decent job, we know we can improve the approximation simply by increasing the number of rectangles, right? If we increase the number of rectangles, each rectangle will take up a smaller space and it will adapt to the changing pattern of the graph a lot quicker. So then taking that concept, then what if we keep increasing the number of rectangles from 4 to 8 to 16 to 100 to 1,000,000? And so what we can convince ourselves then is that our approximation will be better and better the more rectangles that we use. But are we able to maybe do something better than approximation? And the idea is, what if we push the number of rectangles out to infinity? If we do that, then we're able to move from just an approximation to conceptually the exact area under the curve. Okay. And the way that we're going to push the number of rectangles out to infinity is we're going to use limits to help us with that process. Okay. So now moving on to this formula that we'll be using. Okay. I want to show you that with this formula, there's a width component, b minus a over n, and there's also a height component, f of a plus b minus a over n times I. And what's going to happen is you see that summation here. That summation means that we're going to be adding multiple pairs of width and height. So we're going to be adding a certain number of rectangles. And that's what that n represents, a certain number of rectangles, a certain number of intervals. But we're leaving all these as variables because we're going to, after we get that set up, we're going to push that n out to infinity. So basically, we're going to be adding infinite number of these width and height component that build the area of each individual rectangle. Okay. So within the height component, there's a lot of things going on here. It's starting with the left endpoint, and it's going to increment to the next interval over. So a plus width times I. Each time I gets increased, we're able to find the next interval over. So we were doing all this by hand yesterday, right? Yesterday, we spent the time to find that left endpoint, which was 0, and then we used the width to increment over. We added to get to the next interval over. So we added 1/2, and we put 1/2 down. We added 1/2, we put down 1. We added 1/2, we got 3 halves. And then we had to insert them into the function one by one. But now all this is going to be self-contained and done all within this formula. So we're not going to have to do each individual interval by ourselves. It'll all be done within this formula. Okay. So let's try example 1. We're going to be using this area formula to find the exact area under the curve from -2 to 2. And really it's not that important to see what the graph looks like. We just have to apply, we're just practicing applying this formula. Okay, so the first thing that we need to find is we need to find this width component. Okay, so the width is b minus a over n. And then your a and b values will be provided for you. Those are going to be your endpoints. So our width is going to be b minus a, so 2 minus a -2 over n. Okay, we combine this together, we get 4 over n. And what we need to recognize is that we don't want to replace the n with the exact number of rectangles, right? Because we want to leave that as a variable because we're going to push that number out to infinity. Okay. All right, so now I'm going to start putting the pieces in to my formula. Okay, my width component is 4 over n. And then my height component, f of my left endpoint, I'm starting at my left endpoint, which is -2, and I'm going to keep adding the width to reach my next interval. All right, any questions up to this point? All right, so eventually we do want to combine these together, right? We want to combine the width and height component together so that we can get something going and we can eventually evaluate the limit and work our way down to a numeric answer. But the problem right now is that this is not the same, but it's not, this is a function notation. So function notation, we can't just merge this together. We have to find a way to get this out of function notation. So we have to involve our specific function because this specific function is what's going to tell us the specific heights at particular values. So we have to somehow involve this argument into this function. All right, so I feel that this is where I see students struggle, knowing how to involve this, get this out of function notation and into this function. And I think something that helps is creating a bridge that will help us see how this is going to fit inside. So imagine this entire -2 plus 4 over ni is going to be the argument that's going to replace the x of my function. Okay, so to help you see that, maybe rewrite the function with a parentheses where the x was. So remove the x and put a large parentheses and leave a gap where that x was. So instead of 4 minus x squared, let's write it as 4 minus parentheses squared. Okay, do you see that connection there? 4 minus where there was an x, I'm now leaving a gaping hole where that x was. But my my structure is still the same. It's still basically 4 minus x squared, but now I'm leaving a space where that argument is going to go. So now I can replace that gap with my argument. So now f of -2 plus 4 over ni is same thing as, or for this problem, it's going to be 4 minus -2 plus 4 over ni squared. Okay, do we all see the connection from here to here to here? All right, any questions so far? All right, so now this is now going to replace my f of -2 plus 4 over ni. All right, so okay, my width component and then my height component. Now we're going to be spending our time trying to clean all this up. So I'm going to FOIL this out, clean all this up, distribute the negative through, combine like terms, involve the width component. And once everything is cleaned up, all the parentheses, the exponent, the brackets are all resolved, then I can explore my summation formulas, convert everything in terms of n, and finally find the limit. Okay, so I'm going to spend the time to FOIL my parentheses out first. Okay, FOIL this out. So I get 4 combine some like terms here in the middle. And while I'm combining like terms, I'm also going to just go ahead and distribute the negative through. So I'm going to change the sign of everything inside. Remember, there's still a width component outside this 4/n. We see some things that we can take out. The 4 minus 4 will go to 0. And my last set of bracket parentheses, I'm going to distribute the 4/n through. So 4 times 16, all right, it's going to be 64. All right, any questions up to this point here? All right, so now this should become more familiar because we were doing this on Wednesday, right? We're going to assign each term with their own summation. We're going to isolate the summation portion of our rule, of the summation I squared, convert everything to be in terms of n, and then pick out ratio of coefficients, and then find the limit. And I'm also going to start pushing the coefficients out as well. Okay, replace the summations. And we refer back to our summation rules that we learned a couple days ago. So we have n times n plus 1 over 2 for summation I squared, n times n plus 1 times 2n plus 1 over 6. Okay, we talked about a little bit of a shortcut where we can just find the most important term from the numerator and ignore the lower degrees. So I'm just going to get the 64n and n to combine. And likewise over here, I'll get 64n, n, and 2n to combine, and that's all I need from their respective numerators. (64 times n times n times 2n), I get negative 128 n cubed. Right. There are a few more terms that we're not going to have to spend time to find because we have everything that we need already. Okay. So we have matching degrees, which is what we're expecting. Take the ratio of the coefficients. 64 over 2 is just 32. Clean this up, and we get 32/3. So this is not only an approximation, this is basically involving infinite number of rectangles to find the exact area under our graph. Okay, any questions so far? All right, I'll recap the steps, and then we're going to talk about another set of approximation, which is using trapezoids. And then if we have time, we'll come back and we'll do another one of these problems to get some additional reps under our belt. But let me just kind of recap a bit here. So first we started with identifying the need to find the width, which is pulling it from our left and right bounds, our a and b value. So we find our width, b minus a over n. We leave n alone. We leave n as a variable. And then we start to put this into our formula. So replace the b minus a in terms of our specific left and right bound. And also we're going to have to start off our left endpoint so we can know where to start to build our increments. So once we have that, then we have a width and height component that is clear for us to see. But before we can merge this together, we have to get this in a more suitable form to be able to combine with this 4/n. We have to get this out of function notation. So to get out of function notation, we have to involve this particular function, which is giving us the specific heights for this particular problem. But we have to know how the argument is going to be used inside the function. So to help with that process, rewrite the function with a set of parentheses where the x was. So rewrite it as f parentheses is equal to 4 minus parentheses squared. If you can get this to show up, then it helps a lot more to know where this expression is going to go. It's going to go inside the parentheses that you just created. So f of -2 plus 4/ni is equal to 4 minus -2 plus 4/ni squared. So now we have something that is a replacement for my function notation. I get it out of function notation, and then I'm going to make sure I follow order of operations to be able to expand out correctly. So keep expanding, and then little by little, we're going to begin to resolve these parentheses. And then the brackets, combine like terms. Don't forget, the width component is still going to be distributed through. And once you have everything cleaned up, we should have everything in terms of n and i's. Then we're going to use our summation formulas, push out our coefficients, isolate the parts that will be replaced with the summation rules. Everything is now in terms of n. Pull the information that we need from the numerator, and then we get our fraction that represents the area, and we get our answer. All right, so let's look at 4.6, where we're going to finish up with one last set of approximation available. So we learned about the different ways that we can create rectangles, inscribed rectangles, which is like lower sum, circumscribed rectangles, which is like upper sum. But these are involving either the left or right endpoint of each rectangle. And then we found an even better approximation, which is using midpoint rectangles, where we can help ensure that if we attach the midpoint of each rectangle height to the curve, then we have portions that stick above and below, which is just naturally just going to be a much better, closer value to the exact area. But today, trapezoids, we're going to see that because the way trapezoids are shaped, it's just naturally a better mold for the shape of the graph. Now, maybe you have seen trapezoids maybe drawn this way, where you have parallel bases, parallel horizontal bases, the height being the vertical component, and then maybe there's a slanted portion of the trapezoid. But to make it fit our orientation for our graph, we're actually going to we're going to kind of flip this trapezoid on its side. Right. So now, instead of the parallel components being horizontal, we're going to make the parallel components being vertical. And then the horizontal, the height is now going to be this horizontal base. So our formula, instead of 1/2 height times base 1 plus base 2, we're going to rewrite it as 1/2 width times height 1 plus height 2. So we're just kind of flipping the base and the height around. Okay, still the same shape, just the orientation is a little bit different. Okay, so here's example 1. It says estimate the area bounded by our graph 6x minus x squared. That's this upside down parabola. And the x-axis using 6 trapezoids. So first thing we need to do is we need to find where these endpoints are, okay? Because that will help us find our a and b value. So to find our endpoints, we're going to set the function equal to 0 and look for the x-intercepts. Okay. We want to know when the 6x minus x squared is going to touch the y equals 0. So factor the x out. So we have 0 and 6 being our left and right bound. And now we want to find the width. We want the width to be the same for each of these rectangles, or sorry, trapezoids. So b minus a over n, same width formula as before. Our a value is 0, our b value is 6, and then our n value is 6 because we have a specific number of trapezoids. Six over 6 is 1, so our width is just a whole number. So starting at the left endpoint, I'm going to keep adding and find the values of these intervals. Right, from here, I'm going to start applying my each of these regions. I'm going to create an area of trapezoid formula for each of these. And the area that we're using is 1/2 width times height 1 plus height 2. So with each of these endpoints here, we're going to extend these vertical heights all the way to where the graph is. And then at the top of these heights, we're going to connect all the tops of the heights together. And you can see that we have trapezoids all the way across. Now, you may be thinking to yourself, wait, these look like triangles, okay? The first and sixth, and they are. But we don't have to worry about creating a different formula because notice that this height is 0, so if one of the heights go away, it just turns itself into a triangle formula, right? 1/2 width times height, 1/2 base times height. So we don't have to worry about creating a separate formula for the triangles. It will just work itself out. But if you notice that most of these are trapezoids, and the way that these trapezoids are shaped, look at how minimal the gap is already just by using a few number of trapezoids. Imagine if you're trying to connect using rectangles, you're going to have a lot more gaps than 6 trapezoids. Okay, you can barely notice these gaps, very minimal already. All right, so we know that this trapezoids, assuming that we have the same number of intervals, trapezoids is going to be the best way to approximate the area of a region. Okay, so I'm going to start building each of these areas of these separate regions. So first step, my first region, there's a width of 1. So 1/2 width of 1. Height 1 plus height 2. I'll use f of 0 and f of 1 to represent the height. Moving on to my second interval here. Still 1/2 times width. The width is all the same. But now I'm using f of 1 and f of 2 to represent the heights of my second trapezoid. Okay, we go down the line here. All right, there's quite a few that we have to do, right? And then there's a final one. I'll just skip to the end. 1/2 times 1, f of 5 plus f of 6. Now, using trapezoid approximation, it's fine to write all these out, but there's actually a faster way or a more condensed way of representing all these separate areas. And one thing I notice is that I have a common width and height for each of my trapezoids. So what if I factor my width and my height out in front? Then I just have to write it out just once. And then all the heights are free to merge together and combine together. But do you see a pattern from the heights that are being used across all these regions?
The second height is usually the first height of the second.
Okay, continue with that line of thinking. So what pattern do you see?
So like, for example, for the first term, it was f0 plus f1. The next term is f1 plus s2, and then 2 plus 3, and 3 plus 4, 4 plus 5, etc.
Right. So all these heights are, most of them are duplicated, right? Most of them are duplicated. But why are they duplicated? What is it about this? Why are we repeating these heights over and over again?
Because, for example, trapezoid 1 and 2 in the parabola share the same wall.
Good.
For f
Good.
value.
Good. There's a shared height, so that's why f of 1 is used twice, because it's used for the first interval, but it's also used for the second interval. Now, are all the heights repeated?
No.
Which ones are not repeated?
The 0 and 6.
Good. Right. The end units are not shared. Right. Those are only used once. So that's the pattern when we go through this, called this trapezoid approximation, where if you know all the heights that are being used, you can just use the ends once and then double all the ones in between. Okay. So f of 0, and we're going to double f of 1. Double f of 2. Okay, still quite a lot to write, but it's a little bit less than having to write them out individually. Okay, so here's trapezoid approximation, not having to write out as many terms as before. So if we want to find the actual approximated area, we got to spend the time to plug in each of these values into the function. F of 0 in here to get the height, get that number. F of 1, plug 1 into the x, get that number, so on and so forth. So we're going to just jump to the end. Our area approximation for this problem ends up being 35. Okay, any questions here? Okay, so we jumped all the way to 4.6. We're going to go back and do 4.3 to 4.5, or 4.3 and 4.4. But because we're jumping to this 4.6, in your homework, there's going to be some notations that that has not been introduced yet. So just want to kind of give you a heads up there. So right now, you may when you go see when you look at your homework, you may see something that looks like this. Okay, we haven't learned out what this interval notation or this integral notation is yet. But if you see this notation, just understand that whatever's in this space is the function that you're working with. And then these numbers that you see above and below are going to be your A and your B value. Those are your bounds. Okay. So if you see that notation, just pull the information that you need, and then from there you can go through your process. Find your width, find double all your heights except the ends, 1/2 times width, and then do your calculation. Okay, any questions so far? Okay, so with the remaining time, for about 10 minutes here, I want us to do another problem where we can do some more practice with these exact area process. So you can either copy this down or you can kind of just follow along. Okay, so we're going to apply this area limit formula for this particular function given our bounds. Okay, so first thing, we're going to find the width. We're going to identify our A and B values. And we're going to start putting this information into my area formula. So to find the width, B minus A over N, again, we leave N as a variable. We don't want to restrict it to just a specific number because we want to eventually push that number out to infinity. So our width is 2 over N. And now we can start putting, building up our formula here. So replace our B minus A over N with 2 over N, and then we can also replace our A within our height component with 1. Okay. All right, good so far. All right, so eventually we do want to have the width and height component to be combined together, but right now this is not in the correct space for us to do that. We have to get this out of function notation. So to get it out of function notation, we have to use this function, particular function, because this is going to tell us the specific heights at specific points. Okay, so we know that we'll be working with this y equals 2x squared minus 3x plus 2. And we have to know how to involve this argument into this function. And the way that we're going to do this, maybe as a bridge, is rewrite your function, but instead of the x, put a gap with a parentheses in place of the x. So rewrite it this way. And having it written this way to begin with will help you notice where your argument is going to go. It kind of helps restrict so you're not making a mistake, right? It'll go wherever these gaping holes are going to be. So now every time I see a every time I see a parentheses, I'm going to fill it in with my new argument. So I can replace my f of 1 plus 2 over ni with this new expression here. Okay, so do we all see how we're able to get there? We started with the function, put a gap with parentheses wherever the x was, remove the x, and then fill those gaps with a new argument. So now this is a suitable replacement for f of 1 plus 2 over ni. Okay. Now we can start piecing these terms together. So we have a bunch of parentheses inside. We have some exponents we got to resolve. So careful with your order of operations. We got to resolve this binomial squared before we can multiply the 2. We can't distribute the 2 through and then square. Okay. Order of operations tells us the exponent is going to take precedence over any multiplication. So I'm going to spend the time to FOIL this out, write this out twice, 1 plus 2 over ni times 1 plus 2 over ni. Okay, I'm going to FOIL this out, and then I'm going to work that 2 into my distribution. So 1 plus 2 over ni plus 2 over ni plus 4 over n squared I squared. Combine some like terms in the middle. And then I'm going to start distributing the 2 and -3 through. I can resolve some of these internal parentheses. And as I resolve the internal parentheses, there may be some common like terms that I can put together. So the 2, the -3, and 2 can combine to be 1. The 8 over ni minus 6 over ni can combine to be 2 over ni. So we're getting closer towards cleaning up all the parentheses and brackets. The last thing I'm going to do is to involve the width. The width is going to distribute through my height component. And now I should begin to realize that there is a need for each of these to for me to apply a summation rule, summation formula. So I have summation of each of these terms. And as I do that, I can also begin pushing out all my coefficients out in front. And as I push my coefficients out in front, it helps me see the parts that I want to replace. Summation I squared, I'll replace that with a rule. Summation I, I'll replace that with a rule. Summation 1, I have a rule for that as well. And once we reach this point, then we know that the only thing we need to pull is the numerator with the highest exponent, and we should get matching pairs in each of our fraction. Okay, so if I multiply this through 16 times n times n times 2n, we get 32n cubed plus a bunch of terms that's not going to impact our limit because we already see a matching degree here. 4 times n gives us 4n squared plus another term we can ignore because we already have matching pair. And then 2 over n. So each fraction, we're expecting a matching pair, 28 over 3. So if you come to a point where you get to this part and you realize that you're not getting a matching pair, and your numerator ends up being higher than the denominator, there's something that didn't go quite right. So a common mistake that I see students make is, because most of your work is done within the height component, I think a lot of students, it's easy to forget about the width component, and we forget to distribute the 2/n through, and that's going to cause the denominator exponents to not match. So I think that's a common mistake that I see, where all of our effort is within the height component, and we forget to include the 2/n, and that n is needed to help get that degree to match. So careful that you don't forget to distribute the width component through. All right, any questions? So on Monday, we're going to finish up on 4.2 with Riemann sums. Now there's another part of Riemann sums, or another a way of expressing Riemann sums using table of values that we haven't gotten to. And this is the way that most likely the AP exam is going to ask you to be able to gather information using rectangles, is they're going to give you a table of values. It's not difficult, but we just have to know how to apply it. So we'll finish this up on Monday, and then we'll start 4.1. 4.1 is power rule, which is for integrals. So we know power rule for derivatives. So the process for integral power rule is going to kind of involve the opposite operation that we're used to seeing, because we're undoing the process that we did from first semester. And also that is going to, we're also going to use that process to help us achieve the exact area without having to go through this limit process. Okay, but it's still important that we learn this process to understand the fact that we're essentially adding infinite numbers of rectangles, and we're just using summation and limit to help us achieve infinite number of rectangles that moves us toward exact area. So we'll do that on Monday. On Tuesday, we'll finish reviewing, we'll finish 4.1, and then Wednesday, Thursday, we'll have those 2 days to review for our quiz, and then Friday quiz. If you want, if you feel like you need some more support with these limit definition of area problems, I'm going to spend some time working through some additional problems this afternoon, help session at 3:30. But if you can't make it, just know that it'll be recorded, so you can always check it out if you have time. All right, that's all I have. You guys have homework over 4.2 and 4.6. Check the homework calendar. The link is at the top of the chapter 4 page for the textbook assignments. All right, have a great weekend. I'll see you guys Monday.
Thank you, Mr. Yang.
Thank you. See you guys.
Thank you.
Bye.
Thank you.
Bye.
Have a nice day, Mr. Yang.
Take care. Bye, Jason.